So let me start by just welcoming everyone to today's CDY talk. It's a great pleasure to welcome Sabrina Casanova, and she's going to give us a talk about detecting microquasars with HAWC. And just a quick introduction, Sabrina is an expert on extended galactic sources, relation to cosmic ray astrophysics, and particularly the origin and propagation of cosmic rays in our galaxy. Sabrina did her she actually, as an undergraduate, she did theoretical work in Rome on general relativity. And then her PhD was on QCD, parton distribution functions in Germany. And then she transitioned to astroparticle physics, starting working with Brenda Dingus at Los Alamos National Lab, Sandia. And she worked on Milagro and then later HAWC. And then she went on to work with Felix Aharonian at MPIK in Heidelberg. So she has a long history on working in this field, and she's currently a professor at Krakow Institute of Nuclear Physics, and she's a member of HES and HAWC and CTA collaborations, and she's worked on, going to tell us some interesting results from HAWC on the study of microquasars. So welcome, Sabrina. Just as a reminder to everyone, we'll try to do a 50-minute talk, and then we'll have questions. And usually we try to do that about an hour, and then the last 30 minutes, we just have an open forum of discussions, and Felix is going to lead that today. And I also want to say that, if you're not getting our emails directly, please send us, any one of us, an email, a note with your email, and we will add you to our list. So thanks, Sabrina, and you can start anytime you're ready.
Okay. Can you hear me? Yes, I think so.
Yeah.
Right.
Yeah.
So good morning, good afternoon, and good evening to everybody. So this is the second seminar on the topic of microquasar and gamma ray loud binaries. And I will build on the nice introductory talk given 2 weeks ago by Laura. And I will introduce you to the microquasar detected with HAWC. So, let's see. This is the outline of my talk. I will briefly introduce you to the HAWC Observatory, then a bit of view on our consideration on the cosmic ray paradigm currently, and then speaking about building up on the introductory talk, we will discuss about the role of microquasar within the cosmic ray paradigm. If I have time, I will also discuss the other binaries that we detect with HAWC, and then some conclusion and outlooks. So HAWC is air shower array located in Mexico in a relatively good location, not too north, and it's in Mexico, close to the Sierra Negra volcano. It's at about 4,100 meters above the sea level. It is made of 300 water Cherenkov detectors that are laid out over 22,000 square meters. So the characteristic of this, oh, maybe I take this away. Oh, don't know. Oops. Sorry. I'm making wrong. Okay. So it is already almost 10 years old. We inaugurated HAWC in March 2015. Since then, HAWC has practically observed the sky continuously at about 95%, even more operation time. And the characteristic of air shower arrays is that they observe almost all the time big portion of the sky. Their sensitivity in the case of HAWC is not as good as, for instance, imaging Earth Cherenkov telescope, but it has the advantage to collect continuously photons. The angular resolution is also not fantastic at low energy, but it reached good angular resolution at high energy, up to 0.2 more or less. So on top of these 300 Cherenkov tanks with 4 PMTs, since 2018 we have another 345 smaller tanks all around that you don't see in this picture, all around the main array. So how does it work? So high above in the atmosphere, a proton or a gamma, a photon is producing air shower on the top of the atmosphere. Yeah.
好的，好的，好的，好的。
And okay, and the secondary particle produced by this primary interaction goes down in the atmosphere and reach our tanks. In this case, there is this sketch that was done for the predecessor of HAWC Milagro. What we measure is the time and the different time the air shower touch the detector, and also the light level in each PMT. And what we construct is a core, the energy, the direction, and the background. Sorry, is okay? So, and this, if you are interested, a big step forward in our analysis was done when we introduced PAS5 analysis pipeline, where we really did a lot of work in improving the background rejection. We have a better angular resolution and a better sensitivity, especially in the lower energy part of the spectrum. So this is just for your reference. If you want to look more, read more about this, this is also the paper published, and this is the 10 years HAWC sensitivity reached with the PAS5 sensitivity. There will be another step starting January 2025. We will have a new pipeline, so-called PAS5, PAS6. It will be the last one for HAWC, and it will include finally also the outriggers data, 6 years of outriggers data. So following up the introductory talk by Laura, I would like to set up a bit the stage for the discussion. So Laura discussed microquasar in relation to their role as cosmic ray accelerator, and I wanted to give also a sort of general introduction to this. So because recently what was the supernova paradigm of a couple of years ago, 10 years ago, is a bit we made big steps in this direction. So back in those days, before say 2015, not so long time ago, there was a research focus. This is my feeling. The research focus was on the local cosmic ray spectrum. And this local cosmic ray spectrum was fantastic. We used to say featureless. It was not so featureless, but pretty much. And it was also very comfortable to have fantastic sources like supernova remnant that were the perfect contributors, because they were providing the right energy budget to explain the cosmic ray population. And not only this, for them, a theory working very well was also established, acceleration theory. And this was one of the biggest example of supernova remnant in gamma rays. But very, very soon after Imaging Cherenkov telescope started imaging object like RHJ, it was pretty much clear that cosmic rays in supernova remnant, at least what we could see of them, were up to 100 TeV. So the cutoff that you see here, plotted in here, of the major supernova remnant known in TeVs, has a clear cutoff of few TeVs. Even including, from the point of view of the theory, even including amplification of magnetic field, it was difficult to pass this 100 TeV kind of limit in the acceleration. And last but not least, high precision measurement really revealed multiple features in the local cosmic ray spectrum. And in the meantime, in the gamma astronomy, really, the gamma astronomy revealed that the highest energy, ultra high energy sky is very bright. I think breakthrough discovery was for sure the Pevatron in the galactic center by HAWC. And also a class of Pevatron candidate discovered by us more or less in the same years start setting the stage really for a change in this paradigm. And then with HAWC, we published a first high energy catalog for sources above 50, 100 TeVs. And of course, LASO made really a major step, a revolution, showing how bright the sky is at even PV energies. And what is very extraordinary is not only the number of sources, but rather the number of classes of sources that have been revealed in gamma rays and ultra high energy and very energy gamma rays. And in this way, slowly the focus of the research migrate to understand what are these classes of sources, how they confine, they accelerate, and they let cosmic ray then escape and diffuse in the galaxy. And supernova remnant haven't lost their role. The question is, what is the role of each of these sources? We know, for instance, that our supernova remnant from LASO and also HAWC, this is boomerang, gamma ray sources associated with molecular clouds close to boomerang. They did not disappear, but the question is, what is the role of all these classes of sources? And the latest discovery are microquasars. And what Laura discussed last time was the role of microquasars inside the cosmic ray paradigm. And we go on with this role. So in HAWC, what do we do to look for sources? Not only binaries, but all the sources. We are a survey instrument. We look at the maps. And we start revealing SS433 in high energy. Then we detected LS5039. LS5039 has been a long time there, but we collect a bit more of sigma now. And lately, V4641 Sagittarius. So we start with SS433. So SS433 is a very famous system. It has a jet seen in X-ray, in radio, and the jet impact in the remnant of this supernova, W50, and produce well-known X-rays and radio jets. So lots of information has been collected on this source. And also we know that it has the most powerful jets in the galaxy. The galaxy, the power of this jet is 10 to the 39, 10 to the 40 ergs per second. And it's known to be baryon loaded, which makes it also interesting for our purposes. Since ever, people believe that he could have been an accelerator, a very effective accelerator of high energy particle. And in fact, already in fact, okay.
Sorry about that, I just muted.
Okay, hope they are not so angry at me. So, and what already EGRA set up important limits on the emission from this object. Then with Fermi, there was some evidence of a persistent emission, and Veritas as well. And S and Magic set up some upper limits on this source. But what happened was the following. Sometimes in 2016, 2017, I don't remember, people start looking at the emission close to this source. This is 1908, a source so bright in the high energy sky that was detected by the predecessor of HAWC, Milagro. And next to this very bright source in gamma rays, some emission was popping up. And once you mask this source, and also half of the sky, including the galactic plane, was excluded. This is the map of the emission that remains from this portion of the sky. So in 2018, this source was the two lobes of SS433 were analyzed together with a post-trial significant just above 5 sigma. But what was interesting from the very beginning is that the emission looks pretty much coincident with the X-ray emission, with this eastern and western lobe. And this is also the first time that people realized that powerful jets can accelerate particle beyond 100 TeV, because the energy of this photon that we detected from SS433 was at least 20, 25 TeVs. And here there is HAWC data point set up. So if we combine gamma rays and X-ray emission from these lobes, back in those days, we had also given this value, this estimate for the local magnetic field. And concerning particle acceleration, the particle acceleration should, according to the HAWC detection, should happen more or less at the termination shock, probably where the X-rays lobes are visible. So where we will see again this location in two more works that I will briefly present you. And the energy budget, very low, very modest for electrons, higher for protons. However, we don't really know the gas density. We don't know how the gas is distributed there. So anyway, this is the what we wrote in the paper, and what is now quite established also by many other, and also with more information. Recently, in 2014, we increased the data set. We included also PAS5 reconstruction, and we could analyze separately the two sources. And the interesting aspect of this is that the lobe spectra reach in both cases 100 TeV. So And in 2022, I think, has made a beautiful study of these lobes of SS433. And thanks to the better angular resolution and also to the high sensitivity in also the energy resolution, they could also revealing energy-dependent morphology of this emission, which in first approach can be seen as evidence for electron acceleration and emission from electrons. And interestingly, the emission at TV energy, at multi-TV energy, is still coincident with the two lobes. And in the same year, there was also another beautiful paper by Samar, where she studied in detail with more information, more X-ray data, the eastern lobe. And she will present her work in a future seminar of the series, but just to give you an idea, the hardest emission in X-rays appears where the jet suddenly comes out, and it's the same location of the emission detected by HAWC and by HAWC. So this is lower and steeper spectra in X-rays are farther away. Here is probably where the highest energy particles are accelerated and then they diffuse. So the second microquasar HAWC discovered in multi-TV is a different case. V4641 Sagittarius is not a very popular, it was not a very popular object until recently. It's well known among X-ray astronomers because it had an incredible outburst in 1999 when it was first detected. So you can read here, its X-ray flux reached 12 Crab in 8 hours. You see in many different wavelengths how the spike, the peak in the emission. And it's also it has also a black hole similar in mass to the SS433. It has a super Eddington accretion. This is the luminosity, the Eddington luminosity, and it has a super luminar jet with an expansion, apparent expansion of 9.5 C. And when it was first detected during this outburst, they immediately look with VLA, and they detected also a very, very tiny radio jet. And there are since then quite a few detections also of quiescent state. So this source happens to outburst more or less every 2 years, and it makes big bangs, and then it goes quiescent, and it stays quiescent in optical 85% of the time, and it is in active state for 15% of the time. And it's not so extraordinary in quiescent state in X-rays. So about the discovery of HAWC. So we were looking at these maps. We are a survey instrument. We look at maps. Once we have the maps, we look at maps, and we saw this emission quite far away from the galactic plane. So no reason to worry about contamination. However, we didn't really understand it could have been. And we spent a lot of time to try to realize what it was. The fact is, it is very bright. And it's very bright, especially in the highest energy, as we will see later with LASO, even higher than 100, 200 TeV. And for us, it had high zenith angle, but this is with PAS5 not anymore a big problem. We can look at 60 degree of zenith. In fact, we look at the galactic center, isn't it? So the morphology, as you can see here, it looks like it could be two sources, two lobes, like the lobes of SS433, but we can't exclude from our poor angular resolution, we can't exclude, this is our point spread function in the highest energy sector. We can't exclude that it could be an elongated, extended source. But the interesting fact that I put here is that if you look at, this is the location of the binary, and if you look at the distance between this source, the southern lobes, and the northern lobes, it's about 80 parsecs. So it's again a very, very extended jet in whatever it is in gamma, much bigger than the tiny arc-second radio jet in that I showed you before. And about the spectrum of these two sources, two lobes, they are hard spectrum, and as I said, they are bright sources. And what is extraordinary about this discovery is that the power law spectra go up to 220 TeV. We also look at possible variation, considering that this source is it showed outbursts and then quiescent state outbursts, and we look for time flux variation over the last 10 years of operation, almost 10 years of operation of HAWC, and we didn't find any variation. We looked, for instance, at MAXI has a long time study of of monitoring of the source, and we look at time variation correlated to outbursts monitored by MAXI. No way. So it seems to be, okay, we don't have great temporal resolution, but sensitivity, but it looks as if these spectra, these fluxes are stable, like the one of SS433, so persistent emission. About the origin of the emission, so I don't know, challenging or non-challenging, but fact is, electrons have to have at least 200 TeV. Let's imagine that they are accelerated at termination shock. We have a certain time to accelerate them, and this certain time to accelerate them has to be shorter than the cooling time, and the cooling time is quite short. So we put a limit on the shock speed of this shock that could accelerate electrons. And yes, the escape time of this particle is quite long. This is not the problem. The problem is that the cooling is shorter than this. And I'm not saying it is this one, challenging or not challenging. If I found it interesting, however, that if we look at PV protons, so if we want to explain this emission with protons, we need to have PV particles. Let's suppose what we did in the paper is we suppose that this particle were accelerated at the termination shock. And we saw what was the relation between the cooling time for PP interaction in these two lobes and the escape time. And this is what is the energy budget need. We need about 10 to the 39 ergs per second, where eta is could be much smaller than 1. It is related to the diffusion that we assume. So if we take a gas density of around 1 cubic centimeter, 1 per cubic centimeter, we reach a total budget of 10 to the 50 ergs. But also the interesting aspect is that this looks very close to what we need to explain the cosmic ray around PV, the population of cosmic ray around PV energies. So about the gas, so meaning can be not so many of, we don't need so many objects like probably SS443 or V4641 to explain the PV energy range of the cosmic ray, local cosmic ray. So we go back to the local cosmic ray flux. So about the density, so when we look at the density, and it's, yeah, there is not very much gas probably. So this is these are again this is the contour of HAWC, and we plot the atomic plus molecular gas. In reality, it's only atomic, because if you look at the molecular gas in the region, you see only noise. So there is probably not a big coverage of this area, because it's very much below the galactic plane. So we are left with a little density. And what else? This is something that maybe I can also skip, but very briefly, our emission is misaligned with respect to the radio jet. So this is just for information. We probably, this radio jet was observed after one of these bursts. In fact, it's observed if one look at the outburst, and then there is this radio jet. Maybe in TV, we look at what we can describe as a climate, whereas the radio observation, these are the radio observation immediately after the outburst, look at the weather. But so going back to what we were discussing about the role of this object as cosmic ray accelerator. Well, recently we saw this fantastic discovery of 800 TeV from this object with LASO. As I said, this object is extremely bright in the highest energy. It's really bright. And if you see, the emission looks also compatible. I put the HAWC contour here and over the maps of LASO. So yeah, this is the same source that continue up to 100 TeV, close to 1 PV in photons, not in cosmic rays. And there is also preliminary result by Hess that Laura discussed. So for more information about this and other microquasar discovered with LASO, you will have a talk, a seminar later on. Check what time is it. So at this point, SS433, we have a plethora of information about the interstellar medium concerning V4641 Sagittarius. We have nothing, and we would like to have some more information. For instance, we would like to have hard X-rays from a region around, for instance, diffuse hard X-rays that could be the byproduct of PP collision. not byproduct, secondary, from secondary electrons, synchrotron from secondary electrons. And we would expect it to be a prompt emission, and we would have to look in this range in energy in hard X-rays. And as I said, this synchrotron would be immediately after, I mean, within few thousand years from the source acting as a pevratron. So, but not only this. So what we ideally would like to have to come to some, I'm not saying conclusion, but some ideas about what is happening in V4641 Sagittarius is a plethora of X-rays, possibly hard X-rays, and over an area that could cover at least partially the TV emission. And this is coming up. So recently there was renewed black hole activity in Sagittarius, V4641 Sagittarius, and immediately both MAXI, that is doing the monitoring, but also Integral look at the object, and also there was a TOO by X-rays, which covered 60% of the ultra-high energy emission, which is very interesting for us to look for diffuse emission around. We have XMM Newton proposal with HAWC and Kaya. And there is also, from the point of view of looking at looking for gas, we have planned and already carried out observation, partially carried out with APEX and Nobeyama. So finally, I saw on the archive that there are also some expecting neutrino flux, and there is for sure Trident that will be able to detect, but probably also kilometer cube net. So at this point, because I want to finish soon and have time to have some discussion, so I wanted to put down a summary, what I think to be the important point concerning HAWC microquasar. So there is, in both cases, probably super Eddington accretion. To my knowledge, it's not clear whether there is super Eddington accretion also in SS43, but for sure in B4641. Jets, one is the most powerful known in the galaxy. The other one is quite powerful as well. Black hole activities, on one hand, SS433 has a persistent black hole activity to my knowledge. B4641 has this outburst, intermittent outburst roughly every 2 years. Concerning the gamma rays, so they both have hard spectra in our data up to 100 to 100 TeV. The morphology of the emission, we don't know for V4641 Sagittarius. In our data, there is a slight preference towards 2 lobes as well, but we can't exclude that it is an extended source. If we look at the cosmic ray implication, these particles should be accelerated more or less in similar location, quite far away from the binary. And the origin of the emission, well, it could be electrons. We see that the electrons, inverse Compton explains very nicely this space-dependent morphology in Hess maps. But SS433, we know, has baryons inside the jet. And we could imagine way to also overcome this high energy budget required. In the case of V4641, as I said, there are similar probably acceleration locations as in SS43. And what one can say is that, I mean, it could be electrons doing it. It could be also protons, especially if we then consider what I will show you later and from the LASO experiment. But the energy budget for hadronic emission in this case, it tells us that really very few of such objects could explain the local PV cosmic ray flux. And so this is the summary of HAWC microquasar. If we go a step forward, I don't want to go into much detail. There will be a talk by Royu, but LASO has now a class of microquasar. They have 5 microquasar, not only this one, 5 microquasar detected at highest energy, very high energy with V46, 41 up to 800 TeV. So I'm looking forward to Royu talk to see what this class of microquasar mean for the cosmic ray paradigm. And I don't know if Rashmi, should I speak already still about 5 minutes about LS5039, or we want to start discussion and you can be there?
Why don't you speak about LS5039?
Yeah, okay. What I wanted to say, I will say very quickly, this is a very well-known source, has fantastic result on the detection of the period. This is a fantastic result. And what we have, again, for LS5039, like in SS43, we have it next to a very bright region, 1825. And this is what is left in the maps if we mask this big region. This is an old spectrum. There is a new spectrum, and we hope to send the paper in the next days out to the journal. The only things that, in my view, it's interested is that it's not the final one, but there are data points up to 100, 200 TeV. And it's also not so faint, this source. And if we look at the origin of the emission, so we are speaking in this case not of a microquasar. It is not clear whether it's accretion driven or could be another kind of binary. But the point is that we are observing the emission in this case close to the accelerator. I mean, for what close for HAWC means, but if we compare our spectrum to HAWC spectrum, that in the highest energy, I'm not saying the lowest energy, but in the highest energy, it continues the spectrum. It's an old spectrum, this one. There is another one much better than this. But what I mean, we can imagine that is the same location of the emission. And so it's close. It's closer to the, much closer to the binary than, so it's another kind of binary, probably, we don't know, but the emission is close to the binary. And I look at an old but still beautiful paper by Kangulian et al. In 2008 that were looking at constraining acceleration efficiency, location of the accelerator, and B field for HAWC with HAWC data. So already with HAWC data, one could have said, independent of any modeling, based on first principle, that the emission can't be very close. And the magnetic field can't be too high unless we have very a very efficient accelerator. And I redid this exercise profiting from the new data that extrapolate the gamma ray emission up to 200 TeV. And if we expect this 200 TeV in photon to be made by electrons, we can say more or less where the electrons where the electrons have to be accelerated. And you can accelerate it almost everywhere, also relatively close to the binary if you have a very efficient accelerator. Otherwise, you have to put this location outside the binary system if you do not assume a very efficient accelerator. I don't know. We are looking at emission that comes much closer to the binary, and within, let's say, 100 binary orbit distance, we have still quite a lot of photon available there. And if we believe that also this object accelerate very, very high energy proton, like also 10 PV, we can even think about P gamma interaction. I don't know. This is because these are photons. The star photon have an energy about 10 eV. So with, let's say, 5, 10 PV proton, you could make P gamma. So this is my summary, which I leave there. And so, yeah, this is all. SS433, V4641, and LS5039. Now we will add some outrigger data. I'm not sure that after LASO revolution, we will make another revolution, but for sure, this multi-wavelength study will help a lot in this search. Okay, and thank you. I'm sorry for continuing for 50 minutes. Yeah.
Thank you, Sabrina. That was great. So we have lots of time for questions. Please, you can raise your hands and yeah, Susumu, go ahead, please.
Yeah, hi Sabrina. Congratulations for the really exciting results. So about the recent outburst for B4641, hasn't there been radio follow-up observations to look for these small scale jet ejections?
I don't know. Maybe Kaya knows. Maybe it's a good question for Kaya. Who else is there that, or for I don't know. Yeah, for Kaya. I think from the people in the call, I would say Kaya.
Yeah, sorry, can I jump in? So I didn't follow up with radio observation, but I met somebody working on Meerkat observations. I think they did follow up with this outburst and maybe in the other outbursts in the past with Meerkat. So they're looking into their data, and then we're gonna have some conversation, but I don't know any details.
I see. Thank you. Well, I'm asking because as I actually asked Laura the last time, it seems the previous observations of these radio and jet, I mean, it's mentioned that the viewing angle might be relatively close to the line of sight and the velocity might be high, but it doesn't seem like a really solid evaluation. I mean, it's not like GRS 1915 where you really see clear proper motion of components. So I think a confirmation is needed on whether what the actual jet direction is and the velocity. So
okay,
but okay.
Thank you.
Thank you.
Other questions? Felix, do you want to take over?
Yes, now, Reshmi, I can. So, questions.
I think Paolo has his hand up.
Yeah, no, I just had a question about how regular the outbursts are, what happens. So is it in the optical that every 2 years something happens, or in X-rays? Maybe Kaya?
X-rays. To my knowledge, it's X-rays. Yes, X-rays. It was first detected in X-rays, and then the other follow. Am I right? I guess Kaya knows for sure, but it's also my understanding.
I think a recurrence time is around 400 days, but it's not quite periodic, but almost every year they outburst in the X-ray band.
Okay,
Yeah.
but it never got as bright as 1999? Is that the really big one? Is that?
Yeah.
Yeah.
Okay, thanks. Thanks a lot.
Ruyo.
Okay, thanks. Sabrina, thank you for this very interesting talk. Yeah, I have a question on this V4641 measured by HAWC. So you show that you show the image in two energies. So one is above 100 TeV, one is like below. So have you found any significant difference in these two energies? I mean, the morphology.
I can show you. Shall I share again the plot? Shall I share again the plot?
Yeah, sorry.
Yeah.
Yep.
So 1 second. Okay, where is it? Here. Oh. You can see it here. Oh. Wow. There is kind of, but I wouldn't read too much into. Yeah. Fact is, at ion energy, as for LASO, we are much better with. So if I had to put a guess, on the other hand, so if I trust the information more on the IS energy. However, I must say that most of the photons, not most of the photons, but a lot of photons are above 100 TeV. And so, yeah, maybe I would trust more this, but I don't want to say, because
okay.
Can you really say, I think we don't have angular resolution to see differences. Yeah.
Yeah, but my point is that actually this for this thought is the energy dependent morphology is very crucial to understand the origin of this emission.
Yeah, we would like to. What about LASO? Can you do?
No, we cannot do this energy dependent experiment.
It may be in a couple of years.
Yeah. But for
not
now,
now.
it's not. Yeah, not now. Yeah.
But by now, I wouldn't read too much. We give only 2 morphologies, but they are not energy dependent. We look. I know we look for energy dependent and space dependent morphology, but no. I mean, we are happy to have it. Yeah.
Sorry, it's just this left figure also is LASO, or is HAWC, or it's.
This is HAWC. This is 100 TeV. This is 1 TeV.
Above 1 TeV.
Yeah, these are
HAWC.
Yeah.
Okay.
If you want to compare it with LASO, I also overlaid.
No. Above 1 TeV, there's a much nicer picture from HAWC, right?
Yes. I have it here. Yeah, I have it here. This is HAWC picture. Yeah. So this is, this is LASO. This is LASO with HAWC contour. I overlaid the 2 pictures, and this is HAWC. Yeah. But the size is more or less the same. Unfortunately, wait. If you look, it starts from 25 degrees. It's maybe the HAWC source is slightly. No, it's not slightly small. I can't see very well, but.
Hi, Sabrina. Can you hear me?
Yeah,
I'm Laura.
Okay, Laura, perfect.
Yeah, I wrote in the chat, but the HAWC image is really above 10 TeV, right? Because that's where the threshold is for the, I mean, if you look at the spectrum, and the LASSO and HESS and HAWC image all seem consistent, especially HESS and HAWC, which is the ones that both fit, because LASSO I think only fits a symmetric model, so it's harder to compare. But in HESS and in HAWC, there's both an asymmetric model and the parameters are consistent. So at least between 1 and 10 TeV, there's no difference.
So
That
this
was my-
is absolutely correct, what you say.
Sabrina, there was
Most of
a
the
figure
fo-
about 1 TeV. That is HAWC, or it was something else?
So
You had
this
is also HAWC?
this is LASSO, but the contour are HAWC.
No, I'm asking about above 1 TeV. There's a figure that is also HAWC, or it's because do you have a really so do you have a sufficient sensitivity about 1 TeV?
As Laura said, and it's absolutely correct, when we write down there above 1 TeV, most of the photons are above 10 TeV. Okay, not below 10
But
TeV.
then this figure, I mean, then when you
we could call it above 7, 8 TeV, maybe something like that. It would
if you don't know one, then say 10. Okay.
Yeah, but most of the photons are above 10 TeV. It's good. Thanks, Laura, for saying this. Yes.
May I ask you, just Laura? I know we should ask last time, but I mean, Laura, this is very interesting shape. Has morphology. It's kind of curved. It's not how to say
Which
this.
one?
It's a bit like this one. It's I mean, by eye, it looks like curved, right? Twice.
So the answer is, at least in a statistical point, no. So the model that I'm fitting is an ellipse that is sort of long and straight, and there's no residual. So this could also be, so there's not significantly, no.
Okay. Otherwise, it will be very interesting.
It would be very nice. Yeah, I know. I checked, but there is no preference for a model that that is a bit curved. Although with HESS, we took more data this year, and I'm now looking at that. So fingers crossed.
So it's limited by statistics?
Yeah. Well,
or not systematics?
Here I'm just looking at statistics, but it's also that like the apparent curvature is not statistically curved compared to one straight ellipse. That's at least not with the
more observation hardly could improve much situation.
Yeah.
Systematics. Okay, so we continue ask questions to Sabrina, of course. So there's Reshmi, Jianli, and Jamie Holder. Yeah.
I have a quick question. So Sabrina, for V64641, do you know anything about Chandra data? Anything on the X-rays for the mapping the jets? Is there any information?
No, I mean,
I know that for V6.
I know there
for the
is
other one.
something. I know there is something, but let me.
I mean, like SS433, which has been well studied.
Yeah. But that, last year with HAWC, we sent a XMM proposal, and it's only recently that everybody thinks it's interesting. But I think there is some Chandra, but it's probably Kaya knows, not probably, he knows for sure. But it was not something really useful for us. We need a coverage of the highest energy. Okay, it would be the highest energy region. It would be nice to have any, but Chandra, I didn't. Kaya, you know whether there is Chandra. I think there are.
You always point at me. Yes, I know something about Chandra observation. It was a short observation, and then now Mitsuji analyzed the Chandra data. No detection. I forgot the X-ray upper limit, but we need a deeper observations with XMM and also wider observations. So that's why we submit another XMM proposal months ago.
Yeah, this time Kaya and HAWC are the PI, so we are optimistic.
Jamie?
I think Jen Lee was before me. Felix?
Okay, thanks, Felix. Thanks for the chance. Sabrina, thanks for the nice talk. So my question is about the RSPD39, the last source you were talking about. In the SCD, I saw that the HAWC has like a the SCD for different orbital phase, right?
Yeah.
So I wonder, does HAWC see any variabilities along the orbit? Can we divide into like superior conjunctions or inferior conjunctions along the phase?
We could. Okay, this is an old spectrum. In the new spectrum. So what we can say is that up to 3 sigma, we can. This is what we will put in the paper. But up to 3 sigma, we see modulated emission between inferior and superior conjunction. Nothing else. Up to 30 TeV. But this is not so different from what HAWC has. I mean, it's not. The truth is that we don't have temporal sensitivity. So, yeah.
Okay,
but,
so the differences can go beyond like 30 TeV for the like 3 sigma differences.
I can't show you the new spectrum, but if we had the new spectrum, if one look at it, it's difficult to say that beyond 30 TeV there is modulation. Probably there is, but with our data we can't say anything. What we can say for sure is that the spectrum, whatever modulation it has or it doesn't have, it goes up to 200 TeV. This is something solid. The modulation.
Okay, I understand. This is all statistics. Thanks so much.
Up to 30 TeV. Beyond, yeah, we say even 2 sigma for, I don't remember, 70 TeV, but it doesn't, I mean, it's not solid, you know, it's, yeah. But 200 TeV, yes, yeah.
Okay.
Hi, Sabrina.
Jimmy.
Yeah, thanks. Thanks for a nice talk. This may be more a discussion point than a question, but I was wondering if anyone had thought about the implications for detecting systems like this outside of our galaxy. And I'm thinking things like the ultraluminous X-ray sources that are known in Andromeda. Obviously it's much further away, but they're also more powerful systems. So it'd be interesting if anyone's done an estimate. With HAWC, with the IACTs.
So my understanding, I'm really, I'm new in this field. I found myself in this situation, but my understanding is that the power of this galactic system, is that they are intrinsically less luminous, but they are closer. So that's the reason why they are objects on which we can really, from which we can really learn something. And they also have temporal behavior that are human. So probably, I don't know, from my HAWC perspective, I think galactic objects are very nice. Of course, with other instrument, it is different, but with HAWC, for sure, we can't do anything. And I guess, yeah, I don't know, maybe some extragalactic people in the call can answer you better. I think these are, so what what I the first time, yeah.
Could you,
Please, Felix, you.
Could you repeat clearly the question? I think I misunderstood perhaps.
Yeah, so I'm not thinking about AGN. I'm thinking about systems like stellar mass black hole systems like SS433, but more powerful. There are some of these that are known in very local galaxies, including Andromeda. And I'm wondering if anyone's done the math, basically, of you know, if you have a system 10 times more powerful than SS433, but it's as far as a local group galaxy, would we have any chance of detecting it?
But Jamie, there are this square works. So take even they are in M82 Andromeda. So if you take 1 megaparsec and divide 10 kiloparsec, it's still factor of 100 square. So you know it will be not so easy. Actually, this source I understand. This 4641 is a microblazar. I mean, that is some people claim that is a microblazar. And I mean, from very general point of view, it looks like, because it's very strong source. If you noticed, is stronger than crab. It's very, very strong source. That is why Sabrina says that HAWC can do anything in galaxy. Of course, it's not true in a sense, because
anything bright.
Yeah, anything bright. So sensitivity issue. But even LASSO, it will be not so easy. But so only one way, if you go too far, to have a large Doppler factor. So
if we're very lucky with the beaming,
the beaming, otherwise no way. I mean, this square. But if the Doppler factor, we know it goes like to power 4. Then who knows? This is an interesting question, actually.
Either that or we build a telescope 100 times bigger. That's the other option.
But on the other hand, you have also
100 times will not help
squared,
because you need you are losing at least 4 orders of magnitude because of this square.
And
so,
there is also the problem that PV photons are absorbed quite, I guess, quite closely.
100 TV will also absorb, but 10 TV, certainly 10 TV should be okay from nearby galaxies. But this is terrible, this square law. But if there are microblazars, then maybe that I think that if you are lucky, I don't think you can build much bigger instruments. So CTA cannot, I guess. CTA cannot, unless this factor delta 4 works.
Thanks.
Rio, you have a question or
just a comment? Yeah, because for sourcing other galaxy, I think the angular resolution is also problematic, because you know, if we detect something from there, we don't know whether they are like a collective emission from all the sources in the galaxy, or it's from like kind of a single very strong sources, a very strong source. So I think this is another problem.
We'll give factor of 10, maybe 100 in the best case, which hardly 100 microblazars from a single galaxy could be direct to us, I think. I mean, everything is possible, but it's very probably unrealistic. And then angular resolution help for sensitivity, but also here you could gain a bit factor of few better sensitivity. What we are talking about, all these sources are at 1 megaparsec. So that is. But delta 4 is a huge factor. And then if you're lucky, then who knows? No more questions.
Maybe one question myself, if that's related to what Jamie was saying, has anybody looked at the center of Andromeda? Because there could be a higher concentration of interesting things there, even though it's far away. Are there any VHE limits on that?
There are some limits, but not terribly deep. Sorry, if you don't mind me commenting.
Yeah, it's discussion time. Okay.
Yeah, well, I mean, one of the issues, so Veritas has some limits. There are old Tigra limits, I'm sure. I would guess there are magic limits. Well, one of the issues is it's quite optically bright, of course, which makes the analysis a little challenging. But it would be interesting to look for longer. I don't know if HAWC and LASSO have published limits yet.
Because that would be interesting, yep. Thanks.
I think we started discussion, right? Already. So I have one comment or question to others. So is the following: we all think that this radiation comes, these extended sources, because of the termination of wind or jet, and it's likely we see that in the SS433. However, generally speaking, particles could be accelerated also in the binary systems. I mean, in the compact, much more compact regions, and then we could diffuse out, and that is another possibility. So SS433, probably this is not the case. We simply see that this termination, I mean, morphology, but cannot be excluded that we have the second component, which comes because if you take very general consideration like HELAS criteria or whatever, going to the very compact parts, we could increase magnetic field and could probably satisfy. So I would say if you don't consider the SS433, so for others, these extended sources, actually that is the one next talk by Ruyo, the Lahasso, but that still could be in principle possibility that is not just termination, could be both, in fact. And in that context also, I want to say that Sabrina wrote this 10 to 39 per second, and because there was a normalization to diffusion coefficient. So, I mean, diffusion coefficient works as well as density, even better. At least we could speculate with diffusion coefficient. Density maybe is not so easy. So I understand your diffusion coefficient you normalized already was quite suppressed, right, Sabrina?
No, it was eta. It was free, but the diffusion coefficient was the one that we expect if we prolong it to very high energy from GV energy.
No, I don't think so.
No,
you did that. You did that for 100. Right?
I show you 1 second.
Yeah, just show the formula because I mean, well, it depends how you increase. I mean, the 0.5. So anyway, that is whatever it is, and even more. So if you go from 1 GV to 1 PV, then 1 GV, 1 PV, 6 order of magnitude.
Yeah.
And
0.5. Yeah, 3 order in fact.
4.3, yes, maybe, but then even more. I mean, you just we know that these compact objects have the particle propagate much slower, so there's a way to decrease the energetics. So if you take the 10 times less, I agree that you could not speculate much with density, but at least diffusion coefficient, we can do that. I mean, we never could detect Cygnus bubble if diffusion coefficient would not be 100 times smaller than interstellar medium. So that is another issue which we should be careful with when saying arguments again, hadronic and saying that could be much energetic is not sufficient. In this case, we should take into account diffusion coefficient. That still there's a room to get more reasonable numbers. At this moment, not reasonable in the sense that 10 to 39 perhaps is too much.
Yeah.
Because sensitivity in more than 1 PV, imagine if unless you have sharp cut of low energies, you'll get a factor of 10 going down, right? But with diffusion coefficient, I think there's a room to get more realistic numbers.
I have a question. If one can imagine that the emission, as you were saying, is happening very close to the binary, could you, since from this object, LASO gets 800 photon, could it be P gamma? Because if you have high energy...
No, Sabrina, this is diffuse. This is diffuse. This is very large source.
Yeah.
So P gamma, in this, its scales are what are scales?
You're right. You're right. You're right. Yeah, it can be only for LS 5039. You're right. Yeah.
No, this is not. But what we're saying is energetic. It's a very interesting issue. I mean, do you need really 10 to 39 or not? And because this is also criticism for so-called hadronic, right? I mean, the origin of radiation, and then it's still we could get them with reasonable diffusion coefficient.
Yeah, this is
before it.
Sorry.
Yeah. Just you just simply reduce this, and then you. Of course. Okay, so maybe others could talk about this issue or not. Like Pasquale, for example. He likes diffusion coefficient small, close to sources.
Yeah, I do. You uncovered me. No, I was actually thinking we're probably forgetting a little bit about the fact that this whole process is taking place very near the supernova remnant. So even if the W50 was not a powerful accelerator, but there must be a lot of particles that were accelerated there, of course, to lower energy. So this jet is actually impinging on something that was already loaded with stuff. And it's definitely easier to reaccelerate than to energize from scratch. So I don't know. I'm not sure whether somebody has already thought about this.
But what about V4641? There is no
Right. I'm not trying to find generic explanations of all this. We don't even understand exactly what's happening in the different cases, if it is the same process or not. But at least in this in this case, it looks like we have evidence of the two jets hitting the supernova remnant, the leftover of the supernova remnant, actually changing its morphology quite a bit. And if there were particles there in the first place, then it is possible that we're looking at reacceleration rather than acceleration from scratch, which might solve some of these issues at least.
But Pasquale, question was a bit simpler actually. Energetics, right? So this power, what is written here, you see, this is really huge, even for SS4. So what my question was, actually, there are two comments. I mean, we should not ignore the possibility. So there are two questions: the total power in the protons and maximum energy. So maximum energy, with some assumptions, we could get in the extended part, like termination shocks or whatever. My question was, we could also have them very close to the object. We simply could speculate with magnetic field. I'm talking primitive, like Hillas condition, right? So in that case, getting a much larger magnetic field, we could get also just in the, so in that sense, situation will be not, could be different. Of course, maybe not like this ellipsoids, I mean, elongated one, but also that could be connected also to the anisotropic diffusion. I mean, just rather than the hydrodynamical structure. And so that is one.
Yeah, but the magnetic
Yes.
field in the acceleration region might, I mean, here we're talking about something that is moving at a third of the speed of light. So there might be substantial self-generation, not extended over a large region, but just focused in the acceleration region. That's one thing that I was thinking about. So the diffusion coefficient or the magnetic field that you measure on large scales might have little to do with the acceleration part where the particles are being energized. So in terms that addresses the issue of the maximum energy as you mentioned. The other thing is that if really the jet is hitting the remnant of the supernova, then the density might be substantially larger than the standard 1 particle per cc. So the energetics, I would say that can be at least a factor of a few lower than this. Because the downstream of the shock had a much larger, somewhat larger density compared with respect to the interstellar medium. So I'm not sure. So what is the number? What is the number that you would value as reasonable for the luminosity? I'm not aware of what is the typical luminosity of this object.
Adding to luminosity
is 10 to 39 per second, for example. So, but this is entire energy.
Yeah.
Now, could get it in one? Now, the requirement is 1 PV. What? So now we should deal with that. What I'm saying, it's not so easy to play with density. Okay, you said it could be a bit higher. I agree, but I see a lot of potential in diffusion coefficient.
No, I agree. Yeah. For the same reason why the maximum energy could be higher, right? Because it could be substantially self-generated.
Yeah, that was I was saying. I mean, they could be even connected. I mean, and another comment in the same context, you know, we are talking all the time about the jet, but probably you have seen papers by Andrei Bikov and collaborators, and they are arguing that actually this is not, you could have a more or less similar picture with the winds. So Andrei is here, probably he could comment on that. Do we need really jets?
In our model, we have jets 1/3 of C as discussed, but the difference is what we also consider a situation when super Eddington accretion produce a wind. It's not stellar wind, it's a wind which was predicted by some models from black hole itself. So black hole emit two outflows. One is collimated, is jet, which you are talking about, and second is more isotropic flow. And we consider acceleration at the point there with jet collide with wind from the black hole. And there, as Pasquale said, we amplify magnetic field much larger than 20 microgauss, 200 microgauss. And also, as Felix correctly said, we assume what diffusion coefficient can be smaller than 10 to the 30 because of obvious reason in pulsar wind halos, it's assumed to be less. But here we have much larger luminosity of the source. So it is possible to speculate about that.
And proton.
Yes.
Yeah.
So there is a component, a wind component in super Eddington accretion then.
Right. We made a model where there are two kind of outflows from the same accretion disk. One more or less isotropic, and second is the jet, as we all discussed. And idea was what we have reclamation shocks at the position where jet collide with isotropic flow. And position are more or less consistent with what you need.
But it is also consistent with the position of the remnant, right?
Pascal, it's a bit closer. It depends on parameters, of course. We cannot say for sure what is the power in isotropic wind, and but in setup what we simulated with Churazov, it was a bit closer to the source.
But let's put it this way: I mean, at least in terms of the maximum energy, if you just take the parameters of a supernova remnant, and instead of adopting 5,000 kilometers per second, you take 0.3 C, there is more than enough room, of course, to reach much larger energy. So I think the game breaker here is the very high velocity of the jet. So in that sense, I'm not particularly surprised that the maximum energy is high. Of course, the luminosity in well, it's not even so. Even if let's assume that the gamma rays are leptonic, who cares? Let's assume that it is really the product of the leptons. It doesn't mean that protons are not accelerated. It's just that it just means that the emission is smaller, but there could be still more than enough protons to have an influence, to have an effect on the galactic cosmic rays, right?
Pascal, this is exactly what we were saying. What emission at the moment when we were doing this model, we had only X-ray data. Basically, we use basically then. So we were considering Kryptonic scenario to explain synchrotron radiation from new star, Chandra, whatever. And indeed, there we have something like 100 TeV or more maximal energy easily for electrons. And then we speculate what for protons that will mean PeV and more, and with protons could contribute to population. The problem, as usually with anisotropy, of course, Sabrina correctly say what flux can be matched by a few sources, but I don't know what about anisotropy.
Yes, that is true. But okay, that will be next seminar when Rio talk also. I think on you could find in the archive. So energy goes for this at least 41, the 46. It goes to 800 TeV. So that you could have a problem. I mean, of course, it's correct. I mean, you don't need for protons to emit. I mean, they could be also accelerated. But if now you go to 800 TeV, you have to think how to get this 800 TeV with electrons. But anyway, so that will be next seminar. Now Lhasa results. And I want to remind that we have another seminar, more general multi-wavelength, but I guess Samar will put emphasis on X-ray first of all. And to summarize here, we for a long time thinking about supernova remnants. Still, there's no direct evidence. Even I don't think we should say no. It still is ongoing activity. Now arrive these teleclusters. And now we have these guys also. Before we didn't have anything, but now we have even. So the question is just how much they contribute. They could contribute to cosmic rays observed, could not. It's not the most important issue. They are important in their own right. I mean, interesting, right? It does matter how much they contribute. So that is, now we have real labs. I mean, you should not guess. We see everything is going. Even you could see the morphology. So things are getting extremely exciting, actually. And so we'll have another two seminars devoted to microquasars. Okay, we should close now, right? So thank you very much. So we'll have the next seminar again by Rio about LHAWC discoveries of microquasars. Okay, bye.
Bye-bye.
Everybody.
Thank you.
Thanks. Thanks for the nice talk.
Goodbye. Thank you.
Ciao, Sabrina.
Ciao.
Thank you.
Ciao, grazie.
Excellent. Ciao.
Ciao.